as we've seen in our direct comparison test, we're often looking to compare with that reciprocal power function, something of the form 1 over x to the p. And one problematic thing is when you have an integral that contains natural log, because natural log is not a polynomial. It doesn't have a degree, so it's not obvious what you would compare it with right off the bat. So I want to establish two facts about natural log that I think will make it easier for you to do direct comparison tests when the integral contains natural log. The first is I want to prove something about the growth rate of natural log by comparing it with a power function of any positive power. So what I want to look at first is natural log of x versus x to the k, where k is any number bigger than 0. It doesn't have to be an integer. So it could be the square root of x, cube root of x, 10th root of x, millionth root of x. This could be a very, very small number, just so long as it's slightly bigger than 0. So anything bigger than 0. So first of all, let's look at how they compare out at infinity by taking the limit. So let's look at the limit as x goes to infinity of natural log of x over x to the k. Remember when we were doing L'Hopital's rule, I said that this is a way that you can talk about the rates of growth, right? If the thing on top grows faster, this is going to take off to infinity. If the thing on bottom grows faster, this is going to pull down to 0. And if they grow at the same rate, you're going to fall into some constant, bigger than 0 but less than infinity. So remember, natural log does head off to infinity, right? And x to any positive power, we know, grows to infinity. So we have a form, infinity over infinity, which remember is one of our L'Hopital forms. So we can apply L'Hopital's rule to that, which I will do. And derivative of natural log, 1 over x. And this is just power rule, right? The exponent comes down. Lower that exponent by 1. So we have that by L'Hopital's rule. But now let's simplify that expression. That x is on the bottom with that k times x to the k minus 1. So when you combine x to the first and x to the k minus 1, k minus 1 plus 1, you're back to k, right? This simplifies down to 1 over k, x to the k. K is just some positive number, and this thing grows to infinity, so that thing is heading to 0. So what we've established is that natural log of x actually grows slower than x to any power. No matter how small that k is, it could be the 1/billionth root. It's a very slow growing function. Natural log of x still grows slower. Remember my example about Alpha Centauri, right? That natural log grows very, very, very slow. So how does this relate to direct comparison test? Well, think about this. If that ratio heads to 0, eventually it must be less than 1, right? If it's getting closer and closer and closer and closer to 0, we know that eventually that ratio, natural log of x over x to the k, is going to be less than 1. Sometimes in math talk we say for sufficiently large x, right? Once you get to a certain x value, this is going to be true, and then it's going to be true from then on. Well, now multiply both sides by x to the k, and we have an inequality. Natural log of x will be eventually less than x to the k. And this is how you can do a comparison in DCT. So if you've got a natural log of x in your integral, you know that you're allowed to set up an inequality with x to any power you like. And this is nice because it gives you the freedom to pick the degree, so it works out nice for your argument. So as long as k is some positive number, you can argue that, now it may not be true at first, right? The the fact is that eventually this inequality is true. But when you think about direct comparison tests, out at infinity, we're trying to argue something about the tail, right? Way out there at infinity, I think converging or diverging. And so the fact that this may not be true at first is not a problem. This is still useful, even if we have to skip ahead to x equal a billion. If from a billion on this is true, and we could make an argument about the tail being convergent or divergent, then that finite part we skipped doesn't really make a difference. So this is a very nice comparison here for getting a comparison started with power functions. Now, this typically works great when the integral you're looking at actually turns out to be convergent. The other comparison you can do that's somewhat trivial, but just don't forget about it, is that on the flip side, for x bigger than e, natural log of x is bigger than 1, right? Remember, natural log of e is 1 by definition. And so once you're past that, that function's bigger than 1. So you really have comparisons two different ways. If you need to get an inequality going this direction, you can say, well, I know natural log of x is bigger than 1. But if you want to put an upper bound on it, you can argue that it's less than x to the k. So one or the other. It allows you, in instances where you want to put a lower bound on it, you can do that. And for instances where you want to put an upper bound on it, you can do that. And so you'll typically be using something like this to argue in the process of arguing divergence, because your unknown thing is going to be bigger than something. And here you're making this argument, the right-hand side here, in an argument about convergence. So feel free to use either of these. You don't have to go through and argue this every time. You can just say that we know natural log of x is eventually less than x to any positive power. And we know that natural log of x is greater than 1 when x is greater than e. So we'll just to be precise, we'll say eventually. So whenever you're encountering natural log of x, keep these inequalities in mind.